I'm Nikita. I'm a software engineer at Anyscale on the Observability team. This talk will be covering how Ray solves the main challenges faced when doing distributed ML training, both from the actual scaling and performance side and also the observability and user experience features. So a bit of context on what Anyscale does. We provide a platform that makes building AI applications and scaling up to production simple. We built Ray, which is an open source library that's used to orchestrate users' ML workloads. And the Anyscale platform handles the infrastructure to make this more efficient. My team works on the native observability features on this platform, which enhance the user experience. And I'll be showing some of the key features we created in this talk today. So by the end of this presentation, I hope to show how Ray is the best tool for distributed ML training, a high-level agenda. So we'll start by going over common workloads that are run when looking to scale ML training and show orchestration as one of the main pain points across these workloads. I'll then give a brief intro on the core concepts in Ray and show how they provide the flexibility and performance required for a unified orchestration framework. And then we'll talk a bit about why observability is important for the developer experience and why it's challenging to build in a distributed orchestration system like Ray. And then the last part will go into more details on the Ray observability workflow and share some of its solutions to address some key pain points. So every time a new foundation model is in the news, we see yet another example of modern ML models trained using datasets that are too large to fit on a single machine. And we're seeing this to be true for smaller, more specific use cases also, as companies collect terabytes of data for training. The only way to train these models in a reasonable amount of time then is to scale up horizontally and parallelize the training process. So the next couple of slides will give a high-level overview on the types of workloads that are typically run when doing ML training, specifically across multiple nodes. And then we'll highlight some of the properties that a library that's well-suited to scale this type of training should have. So before the model can be trained, data needs to be loaded on the appropriate machines in the cluster. So having a scalable data loading process becomes very important, and it directly impacts how quickly and efficiently models can be trained. So a lot of modern ML applications need very large data sets, and these far exceed the memory of a single node. So distributed data parallel training, or DDP, is commonly used in these cases where the model is split up amongst a number of nodes in the cluster, and different subsets of data are used to train the model on each node. And then at the end, the gradient results are combined. So there are a number of frameworks like the PyTorch data loader, which support data parallel training very well. But then when users are running their code on clusters of different sizes, they'll still have to manually set the dataset partition indices each time. We typically see users do this when they're sanity checking their methodology, like on smaller clusters during development. So to support variable cluster sizes using the same code, the data loader should take into account the number of available workers and determine how to partition the dataset accordingly. So given the cost of compute resources, we want to minimize the time they're kept idle waiting for the results of a previous step. This applies throughout the training process, but the data loading step is one place which could keep resources that were intended for training idle. Streaming data through the training pipeline is one way to increase the utilization and therefore decrease cost, and it allows data loading and training to happen at the same time. This step requires each step in the pipeline to be treated as a fine-grain unit of compute so that the results can be passed through the graph as they're available. And then finally, some applications like image models have a number of per iteration pre-process steps that are CPU bound usually. So this could include things like cropping or rotating or resizing. So if we're using only GPU nodes for these type of applications, we would need to provision a greater number of nodes because the number of CPUs that's available would be limited by the CPU to GPU ratio on each node. And GPU nodes are very expensive, so adding more of them to just speed up the CPU-bound operations isn't very cost-effective, and it instead makes sense to scale up the CPU-only nodes for pre-processing tasks. And this results in a cluster that has heterogeneous resources. So then on to the training part of it. So after the correct data subsets are loaded on all of the machines, the next step is to actually perform the model node training. There are a number of training frameworks that utilize GPUs and other modern accelerators, and we previously talked about PyTorch's strong native support for running DDP or FSDP, which is model parallel training, across multiple GPUs on a single machine. But when further scaling to multiple nodes, the training run would have to be started on each machine manually, Or it's more common to use some workload orchestrator like Slurm or Kubernetes to do this. So these tools do work well when set up correctly, but learning how to use workload orchestrators can be a significant effort. And multi-node training is a pretty common pattern these days, so actually orchestrating the training, regardless of cluster size, should be abstracted away so that there's a lower barrier of entry for all researchers. So to produce a useful model, the training step doesn't just happen once. There are a number of hyperparameters that affect the training process and ultimately the model performance. So the training function has to be run at least partially for many times. Trials can be run for non-uniform amounts of time using techniques like early stopping, in which case additional trials should be scheduled to prevent the resources from sitting idle. And resources required for each trial may not neatly correspond to the resources on a node. So in this example, we see each trial mapping to 2 different nodes. And in more complicated cases, the different trials could have different resource requirements altogether. So to effectively perform hyperparameter tuning, the system must also be able to treat each trial as a fine-grained unit of compute. And although training speed and efficiency increases as we scale to multiple nodes, this also gives more opportunities for failure. So at the process layer, we see errors like out of memory and runtime errors raised from the user code. And then one layer up at the node level, we could also see various hardware failures or network failures. And if the training run is being executed on spot instances, those could also get preempted mid-run. So given that failures are expected to happen, a library should have retry behavior that recognizes when a failure happens and requests new resources and restarts the training run from the last checkpointed data. So with all of these steps, we see that there's many system components that are needed to work in conjunction with the ML workload to support training at large scales. And orchestration becomes a key challenge, especially as the various stages of training data deal with different workloads that use heterogeneous resources. We also see these stages are tied to one another, which motivates the need for a unified framework, which can improve efficiency through the pipeline rather than performing each step independently with a different set of tools. And then the framework also needs to be flexible, both in terms of the types of workloads it supports and also the resource types it needs to operate on, because each stage benefits from different patterns. And as new techniques and optimizations are discovered, ML engineers should be able to easily implement and test out those techniques at scale. So the next set of slides will give a high-level overview of Ray and how it solves the functional requirements for a general-purpose orchestration system that's suitable for large-scale ML training. The core set of primitives that Ray exposes are very flexible, and all the libraries are built on top of these. Python is the most popular language for developing ML models, and ML engineers already use Python functions and classes as a general interface that supports all types of workloads. So in Ray, these are naturally mapped to tasks and actors, which perform stateless and stateful computing in the distributed setting. So Ray runs tasks asynchronously, and the futures that are references to the outputs are returned. The objects that are referenced by these futures are stored in shared memory to minimize the data transfer costs, especially when multiple worker processes need to access these. And the Ray core backend components are written in C++ for more efficient execution, and they integrate with the Python interface for ease of use. So developers can specify the resources needed for each task and actor right at the application layer. This makes it super easy to have fine-grained control over the system behavior, like saying which function runs on which compute resource, without actually having to think about the underlying nodes. Apart from CPUs and GPUs, Ray also supports a number of different accelerators and allows specifying custom resource types. So for example, a custom resource type can be specified to indicate nodes have some specific hardware. And as a result, a single application that's created can be created with heterogeneous resource requirements, but it can still be managed by a single Ray cluster. And because Ray handles the underlying scheduling of tasks and actors, scaling becomes really simple and doesn't actually require code changes. So code can be written accounting for the resources required for a function and then tested on smaller clusters during development. And then the same code can be executed on a much larger cluster in production, and tasks will accordingly get scheduled on the newly available nodes. So this greatly lowers the effort required to run code at different scales and is much easier to get started with, especially compared to other systems where the developer assigns compute tasks to specific machines. And Ray's scaling capabilities become even more powerful because application-level autoscaling is supported. So the Ray autoscaler has knowledge on the compute requirements of each function and that need to run on the cluster. So it can scale up and down with more precision than only looking at the hardware-level metrics. Especially because Ray clusters have heterogeneous resource types, the autoscaler can scale up only the nodes with the resources that are required for the given computing task. So in this example, we see that the GPU node was only launched when the task requiring it got scheduled. And this extends to the data loading workflow that we discussed previously, where there may be CPU-bound preprocessing steps before the data is loaded into the training pipeline. To avoid being limited by the ratio of CPUs to GPUs on a node, Ray can scale up CPU-only nodes for these preprocessing steps. And then the orchestration and cluster management features of Ray, they may seem similar to other workload orchestration systems like Kubernetes. But what sets Ray apart is its application-level scheduling and scaling, which make it ideal for managing how to run fine-grained tasks rather than containerized applications as a whole. So on top of the Ray core foundation, Ray provides a very rich library ecosystem for the most common ML workloads. And these libraries directly solve the challenges for scaling ML training. The requirements we previously saw across the different ML workloads, those are solved at the Ray core layer itself. And they allow libraries to be optimized for their specific workloads. So, for example, Ray data takes advantage of the heterogeneous resources and fine-grained operations as a unit of compute. And this allows scaling up CPU-only nodes for preprocessing. And then another example, Ray train allows the same code to be used to train a model on a single node or a large cluster. And it also has effective retry logic on failures that integrate well with the training checkpoints. So because the Ray libraries all use Ray core under the hood, they also integrate really well with each other. For example, the Ray data and train libraries integrate so that data can be loaded and streamed through the training pipeline. And the libraries allow ML engineers to work with higher level concepts that are relevant to their application without having to know too much about how Ray works under the hood. And this overall makes distributed computing much more accessible to a wider set of developers. So Ray's advantage is scaling at the application layer, but multi-node Ray clusters need some infrastructure that efficiently launches instances for the cluster. So Ray clusters can be deployed directly on VMs or on Kubernetes, or they can be deployed on a managed platform like Anyscale. From the infrastructure side, Anyscale provides a number of features to improve the experience of the ML workload orchestration. Some examples include smart autoscaling and instance selection based on costs or other parameters. We also have out-of-the-box dependency management and multiple deployment options for high availability Ray clusters based on the workload. The behavior of the Ray cluster is closely tied to the behavior of the underlying infrastructure. A good example of this is when the Ray cluster is running on Anyscale and pending nodes. In this case, the Anyscale control plane would have information if there's no more capacity for the requested instance in one zone, and then it can try in another zone and share that information. So as the number of components to orchestrate a complex distributed system increase, so do the potential types of issues. We can see direct failures at the job or node level, errors at the process level, like out of memory, and then jobs may also appear delayed for a number of reasons. From the auto-scaling side, it's possible instances are unavailable, or within a single job, we could see low utilization, bottlenecks, or seemingly random tasks hanging. In all of these situations, it's important to surface the right information with the relevant context, and especially to show it in a timely manner so that the issue can be identified and fixed efficiently. Because multi-node Ray clusters are deployed on some infrastructure platform, an observability system needs to be able to handle errors from within and outside of Ray, and distill the system information back in a way that's relevant for the application developer. And we assume that these developers are not experts of the Ray internals. So Ray's simple Python API makes distributed computing accessible to a wider audience. And this is especially why observability is so crucial, because it directly impacts the Ray user experience by helping users of all skill levels effectively monitor and debug their workloads. So during the rest of the talk, I'll walk through the Ray observability workflow, particularly highlighting how Ray exposes necessary information and integrates with other tools for a seamless observability user experience when running large clusters. And given that Ray is run on some infrastructure, I'll also show some of the Anyscale observability features as an example of what can be done with the information that Ray exposes. So the first main type of observability data we'll cover is metrics. Ray emits Prometheus time series metrics both from the core and library layers. It also provides a simple interface so users can easily add their own additional metrics at the application layer. And Prometheus uses a standard format for metrics, and it still gives users the flexibility to process them using a variety of systems. Metrics are generally an efficient tool for observability because they're emitted directly from the nodes that the data is generated from. And the various metric types, like counters or histograms, are aggregated values, so they can be tracked with minimal performance impact to the application workload. The goal of metrics is to give a high-level understanding of what's going on in the cluster through various aggregated data points. And the Ray dashboard includes several pre-built Grafana dashboards that show an overview of the workload. So some example of metrics at the hardware layer are like node count and CPU or GPU utilization. And these are emitted on interval by a process that's running on each node. We also have Ray resource metrics, for example, the number of tasks and actors in each state, and the Ray object store memory usage. And then at the library level, there's also a variety of metrics specific to the library concept. So for Ray data, some examples include the number of bytes or rows returned by a dataset operator. Logs complement metrics by providing a detailed view into specific events and enabling effective error tracing. Since logs are often the first type of observability data beginners are familiar with, they should be easily accessible. But Ray tasks and actors are run across all nodes across the cluster, and this makes it hard to view logs in a consolidated place. So one way this is solved is by streaming the standard out and standard error logs from the workers to the head node. Log redirection particularly helps with the interactive development case, where instead of having to open each worker process file, the output of the program can simply just be viewed from the script that initiated the Ray application. So next we'll talk a bit about how Ray makes sure that logs contain all of the necessary details for the most common observability failure types. Failures that occur outside of Ray are typically the hardest to provide a good observability user experience for. One example is nodes running out of memory and being killed by the Linux killer. Not only is the error message in this case not in a structured format, such failures can also cause the Ray components to fail. And once Ray components start failing in unexpected ways, it becomes a lot harder for users who are not familiar with Ray internals to parse through these cascading failures to understand the true root cause. So diagnosing exactly which task caused the problem and why the process oomed is already tricky for small Ray clusters, especially when the logs are viewed after the job finishes and the processes are no longer running. But it becomes almost impossible when dealing with large clusters with hundreds or thousands of nodes. So Ray improves the system stability and observability by proactively catching some of these commonly occurring failures. To avoid the node out of memory case, Ray runs a memory monitor on each node that tracks the memory used by all of the components. And if this exceeds some threshold, the memory monitor will kill Ray tasks and actors to prevent the core components from failing. Tasks are usually retried with exponential backoff, but if there's still not sufficient memory, the workload ultimately will fail with an out-of-memory error raised by Ray. And that contains very detailed information of what failed. So we can see in this example, this clearly contains the task ID, task name, node and worker IDs, and memory usage at the time of the error. So users have a better idea of which task caused it. This error is also in a standard format for easy parsing from the logs, and because it's raised from the Ray side itself, we can also emit metrics to track these out-of-memory errors. So apart from the driver logs, there are a number of other log files that are needed to effectively monitor a Ray application. Ray core generates logs that provide more detailed info about failures within its components. And libraries also emit logs that are organized across files based on the higher level library component type. Having separate log files allows several Ray processes to write logs in parallel, but we saw that it's difficult for users to debug an issue that spans multiple files then. So Anyscale solves this by collecting and aggregating the logs in Loki, which is a multi-tenant, horizontally scalable log querying and storage engine. This enables us to provide a unified log viewer experience where logs can be viewed by timestamp, and they can be filtered by attributes or full text search across different log source files. So going back to the out-of-memory error discussed before, sometimes it's possible for the workload to increase in memory faster than the Ray memory monitor can catch it. And the Linux killer would likely kill the process first in this case. So the Ray error message may be unclear, but by comparing the kernel logs and the driver logs for a particular node from the same time frame, using this unified log viewer, we can better pinpoint memory usage as the cause. So logs and metrics provide a lot of useful information, but they're not always sufficient to get an overview of the state of the application or individual Ray resources. Logs can sometimes be noisy and hard to parse, particularly when we care about information that spans multiple log lines, like unique categories of failures. Other times, they may not contain the data we're looking for at all. So in this example, a number of different task exceptions are not actually visible in the logs because the code fails before fetching every task reference. Metrics also have limitations in their resolution because they shouldn't include high cardinality label values like individual task IDs. And this is because Prometheus stores and queries time series data efficiently by creating unique series for each combination of label values. So when a label has only unique values like task IDs, it could cause the number of series to grow exponentially, which would severely impact the query performance and make the metrics unusable potentially. So as an alternative, the Ray dashboard, which is served from the head node of a cluster when it's alive, has a useful task table view that shows the latest state and is created from state transition events. To bridge this gap between logs and metrics for more general use cases, we'll be releasing export events in open source Ray. And these include granular state transitions and metadata for each Ray resource type. In the task example, Anyscale exports events into object storage and offers this highly scalable and persistent task dashboard. Since the events followed a predefined schema, modern database tools can be used to efficiently filter and aggregate task data to extract valuable insights, such as the longest running tasks or unique error types, either like per function or job. And also because the raw state data is exported, it's possible to drill down from this aggregate information to access the resource-specific details. Events can be processed to form a source of truth relationship between the various entities within Ray. So to trace information across the systems, IDs are the first really useful way to link different resources together. For example, the parent task ID field of a task event, it can be used to get more detail on why a particular task is in the pending dependency state. And in this example, we see it's because the parent task is in the pending scheduling state. But outside the Ray relationship graph, we should also consider the interaction between the workload and any underlying infrastructure that's providing the resources. Any issues at the infrastructure layer, like insufficient instance capacity, cascade to the workload. And this could result in the training job being stuck in pending, or it could be killed and restarted. Without easy access to this information, the user would know the state of their job, but they wouldn't know why it's there or if any changes need to be made so that it progresses with less issues. As a heuristic, the metadata in the Ray events can be correlated with observability data generated by components outside of Ray. So for example, we can filter the infrastructure logs by the compute requirements of a task to get instance upscaling logs that are relevant for this particular task. So combining logs, metrics, and events gives us a more comprehensive understanding of the Ray cluster's behavior. But since this observability data is stored on the node that it's generated from, the data needs to be centrally collected somewhere so it can be analyzed as a whole. Persistence is key to improving the observability experience, so users don't have to try to catch an error as it's happening. And because the observability data can't reliably be transferred from worker to head node, even if you keep a Ray cluster alive after the job completes, the nodes may have been auto-scaled down, and this would cause the observability data on those nodes to be lost. Ray emits Prometheus metrics, but then when using OSS Ray on VMs, users would need to set up how to collect and use those metrics. And in general, this can be pretty tricky for auto-scaling distributed applications that have no requirements on the types of nodes that can be included in a cluster, because the Prometheus instance needs to know which nodes exist. Ray simplifies the service discovery problem by auto-generating and updating a service discovery file with the current set of nodes in a cluster, which it can easily do because it has a global view. An external Prometheus server can be set up to watch this file, and it'll always know where to pull metrics from then. Metrics collection is more natively handled with Kubernetes deployments, and the Anyscale platform also uses other techniques to push metrics in a way that's better integrated with the rest of the stack. But Ray Service Discovery is a simple solution, and it still unlocks the powerful insights of metrics without a complex deployment control plane. So the other option for exporting data without a centralized service discovery file is having a process do the exporting for each node. So for logs and events, persistence can be achieved from a number of open source log processing tools like Vector or FluentBit or Promptail, and these would be running on the nodes themselves. At Anyscale, we had good experiences with Vector due to its performance and flexibility to do custom transformations and then send them to a number of different sinks. In fact, Anyscale uses Vector to also scrape metrics from individual nodes and to push them to a centralized Cortex deployment for long-term persistence of the metrics. So if using open source Ray, though, regardless of whether it's run on VMs or Kubernetes, we recommend launching a container per node that collects this data, runs various post-processing transformations, and enriches various fields, and then ships them to a sink that, depending on what the downstream use case is. So putting this all together, all of the observability components can be put together to achieve a seamless experience for library users who may have less familiarity with the Ray implementation details. For Ray train workloads, we use events to get metadata and state change events for the train run, and associated with the train workers, which are tracked as Ray actors. Using the associated Ray actor ID, we can fetch additional details about the actor, such as the node it's running on and various node-level utilization metrics. And these IDs can be used to find additional time series metrics in the Grafana dashboard also. Structured logging and the Ray train's component-level log organization allows easily fetching the logs that are associated with each worker. And then we also associate the requests that are used to schedule train workers with the relevant logs from the infrastructure when it's launching instances. And this helps provide more details when the worker is in the pending state. Because all of this observability data is exported out of the Ray cluster, the entire dashboard is visible even after the cluster terminates, which is especially useful for training workloads where they're run usually as offline jobs. And this is a much better user experience than having to deal directly with Ray worker and driver logs, and then manually having to map to metrics and monitor for any fine-grained issues while the workload is alive. So I hope this gave you a good sense of how Ray provides the flexibility and performance required to be a unified orchestration framework and how it enables the most common workloads typically encountered when scaling ML training. And with the various features to effectively generate and export observability data, along with the patterns that surface the most relevant information, the observability workflow makes Ray easy to use regardless of what the cluster size is. If you're interested in learning more about how major companies are using Ray to scale AI, a quick call out for the Ray and AI Infra Summit that's happening in May in New York. You can find more details in this link. But with that, thank you.